to Fortran over to HIPFort. And I've got some new stuff here. In order to share data with other scientists and research, make that stuff public. You having trouble hearing me?
Yep, no one.
We're good?
No.
Still nothing?
Okay, cut my video. Do you see audio levels?
Yeah. There's audio levels going. So,
Okay.
Okay, we're good. Yeah.
Yep.
We're good to just cut up, so we should be good.
Okay. Sorry about that, guys. We have a few technical difficulties. We're still getting used to doing these live streams, so thanks for bearing with us here. So where I was at is, right, so we're going to talk a little bit about some of the refactoring to meet a pattern-driven design. We did a bit of a transition from CUDA Fortran to HIPFort, and we're also looking at trying to leverage file formats that other software developers and scientists are using for higher order methods. So we'll talk a little bit about Hopper, the higher order preprocessor here, and some of the work we're doing to integrate that tool into Self. And then of course the CLI. The CLI is primarily used for benchmarking and testing, but it does have some relevance for folks who just want to kind of prototype some of the bits of this application just to get a feel for how this works. So to talk about the pattern-driven design, I do want to give you just a brief on Spectre element methods so you kind of have a mental model of what the software layout kind of needs to be to make this happen. And keep in the back of your mind here, everything we're doing, we need to have some availability of this data on a GPU and on a CPU. So to start, in general, when you're working with Spectre elements, you might have a domain. Here I'm showing just a 2D domain, this kind of weird smoothed out star shape. What we do is we divide that domain into what are called elements. And within those elements, you approximate your function as a polynomial. In this case, we're using the nodal form of a Spectre element. So we're using Lagrange interpolating polynomials inside each of these elements. Now, in order to be able to handle complex geometries, each element in physical space gets mapped to a computational domain. In Self, it varies from -1 to 1 in each spatial dimension. And this allows us to do, once we do the coordinate system transformation from physical to computational space, we can actually start to construct divergence, gradient, and curl operators to handle that stuff. So we'll get into that here in the next couple slides. To give you an idea of what the sort of computational layout needs to be when we're doing things like interpolation or taking derivatives, what we do when we say we approximate a function by a polynomial is essentially we have a series representation of a function. Now, if you're doing a modal form, these terms here, the f sub i's, take on a different meaning than if you're doing what we do in Self, which is called nodal form. The f sub i's in a nodal spectral element method are really just the actual function values at a set of control points, and some people also call those control points knots. So if you have that picture in your mind of what that computational element was, each of those points inside that element would be our control points. And in spectral element methods, those are carefully chosen so that you get the desired accuracy. The other function here in that expansion in nodal spectral element methods is the Lagrange interpolating polynomial. Again, the control points where you're taking those nodal values are typically taken as quadrature points so you get desired accuracy. Now, if you want to go to 2D in Self, what we essentially do is just do tensor products of spatial dimensions. So you basically just add another summation here out front, add another Lagrange interpolator out here. This really should be an L sub j, not an L sub I. And then now you've got the nodal points on the 2D grid within each element. And in 3D, you can kind of just repeat that process, right? Now, the cool thing here is, at least in the computational domain, if I want to estimate a derivative of a function in the computational domain, let's say if I wanted to take the derivative of f with respect to this first computational direction, c sub 1, really you just take a prime on that Lagrange interpolating polynomial, and you've got an estimate of that computational, the derivative in that computational space. So you can already see already, because I have these summations inside of here, you can kind of get an idea of how much work it takes to actually do interpolation or take derivatives and remap it back onto the quadrature points that you're working at. And I'm not going to go into a whole lot of detail here, but this is kind of what we're working with. The only other thing I would add here is this is just showing the representation for a single element. In reality, what we have is another superscript here for the element ID for that function representation. So let's talk a little bit about that coordinate system mapping, just so I can give you an idea of how we build on top of this idea. I can represent things in computational space, right? I can map from physical space to computational space and keep track of those metric terms from that coordinate mapping, and we can calculate divergence in a little bit more of a complex way. So if you've ever done differential geometry, this sort of thing is going to look familiar. But the idea being is if I go again from computational to physical space, you can calculate the derivative with respect to physical coordinates, so x, y's, and z's, for example. You can express that in terms of derivatives of the computational coordinates, and you have some modification that you need to do here. And what you're really doing is projecting that function onto what are called the contravariant basis vectors. Now, I'm not going to go into a lot of this in detail today, but we do have some videos planned for later this year where we talk a lot about differential geometry if you're interested in learning more about that. So the basic idea, right, is we have a region of space divided into elements. Within each element, we approximate the function as polynomials. We can approximate the coordinate system mapping as polynomials. And if I can do that, then I can actually calculate estimates of derivatives in physical space. So with that in mind, let's now talk a little bit about some of the patterns that we have in the code that allow us to create the API that's now available for computing solver or creating solvers for PDEs and conservation laws. All right. So at the core of this, go back, right, we need to run on CPU and GPU hardware. So we need a data type that can hold both allocatable arrays and Fortran on the CPU side, and we need device pointers that can host that data on the GPU side. So we create a class called self-memory that has those two attributes in it, and then we have it's really four basic types of functions. We have a constructor, which if you're building for a GPU platform, when you call the constructor, it will allocate the CPU memory and it will allocate the GPU memory. The destructor, of course, would deallocate those. And then you have these routines that are available if you're building for GPU hardware, update host and update device, that you can simply call just to get data from CPU side to the GPU and vice versa. To give you an idea of what that looks like, here's just one of the update device routines for one of these classes. Now, because in Fortran the rank of an array is fixed, we essentially had to go through and define these, I'm calling them HF reals in this case. So real meaning it's a floating point value, and we set the precision using the ISO Fortran ENV module. And then the R5 subscript here means on the CPU side that HF real array has it's a rank 5 array in Fortran. The update device routine, essentially what it's going to do underneath the hood, it's going to use the HIPFort module from AMD's ROCm to do one. It's going to call HIPCheck, which is just a wrapper routine that checks the error codes that come out of calls like hipmemcopy, hipmalloc, and those types of things. And it kind of wraps this boilerplate code so that the users in the end, when they want to update the device data or the host data, they really just have to call a simple API update device. And we actually carry this update device and update host through the more complicated structures. So when you have a mesh, which has really maybe a few different types of HF reals, has some HF ints, you can just call the update device, and underneath the hood, it kind of stacks all those copies for you. So we'll get more into that in a second. Now, once you have the memory defined so you can handle memory on both CPU and GPU, we can start to build the classes that address some of the problems that we need to have solved for doing spectral element methods. So first, everything hinges on Lagrange interpolating polynomials itself. We're doing nodal forms of spectral element methods. So what we need is a class where we can evaluate interpolants, and we need to take derivatives of those interpolants, and particularly we need to cast those in different ways when you get to higher dimensions. So if you want to do divergence, gradient curl, and in 1D do a derivative, we have all those mapped out. Now, on top of just having those routine, the typical type of data you work with when you're doing a PDE solver, and like in CFD especially, we have scalars, we have vectors in 2D and 3D, and we have tensors. And the way this is set up, and I'll just give you one example, and you can check out the code to see how all this kind of works, is let's say I took a gradient in 2D of a scalar. We know the output's going to be a vector. So we have a generic interface for calling a gradient. If you pass a scalar one of the self data types for a scalar, it's going to turn out a vector in return. Now, if you pass a vector into that gradient routine, it's going to turn out a tensor for you. There's other types of logic that comes in for each of those operations that's already handled for you out of the box. And like I said, in the back end, and I'll show you in a little bit here how we actually get the generic interface in place, depending on whether you send a device pointer or a Fortran array into one of these routines, it's going to determine what device that actually runs on, whether it's going to run on the CPU or the GPU. So if you take the cross product of all these possible routines here that we need to do in 1D, 2D, 3D, and with the scalars, vectors, and tensors in 1D, 2D, 3D, this gives you 32 routines that we had to define at the base level. So if we have 32, well, it's really 32 algorithms, and for those 32 algorithms, we have a CPU counterpart and a GPU counterpart. So now we're at 64 routines that are really just forming the core of self. And what happens next is if we have the Lagrange interpolation and we have the data, we can now start to define geometric mappings with that. And so we have a class called self-mesh, which includes some of the geometry inside of there to map those elements from physical to computational space. And if you combine the geometry of the mesh with self-data, we can now do what's called work with what I call mapped data. So you can compute those derivatives, divergence, gradient, and curl in that map space. So you take those 64 routines we had, CPU and GPU side, right? And now we add the component. Now we need to do some mapping there. So all we need to do is add the things for example, contravariant vector projection, things like that. And then we can call back down this whole stack here back to the bottom. So we're limiting ourselves. I think in the end, it's 96 total core routines that make all this magic happen. So here's an actual dependency graph from self. You can check this out on our documentation, which again, you'll find in that README. So again, down the bottom, we control our precision with that ISO Fortran ENV. We've got self-Lagrange sitting here, and that does have some dependencies underneath the hood. Here's that self-memory layer I was telling you about, where we can store basically the interpolants, the derivative matrices, things like that, both on the host and the device. One thing I didn't mention is the quadrature. So there are some support routines in place to calculate Legendre-Gauss, Legendre-Gauss-Lobato, and then the Chebyshev quadratures as well, both Gauss and Gauss-Lobato. Now, when you set the precision in ISO Fortran ENV, that precision really controls all the computations from self-Lagrange higher up the stack. All the quadratures that we compute are always done in double precision, and then they're stored in the precision that you set with the ISO Fortran ENV. As I said, we got Lagrange. If we have the Lagrange interpolants and we have data, and then if we combine that with the mesh and the geometry, we can create this self-map data class. This is where we got to by the end of Q1 here with a lot of that refactoring that was in place, which was again just a CFD solver before. Kind of restructuring it in this light allows someone to say just use this self-mapped data class. They can create vectors, scalars, and tensors, and as long as they load data into those routines using some of the accessors associated with that class, you can start to do computations fairly quickly. Now the next step here is really to add a layer that leverages the self-map data and the self-mesh to do discontinuous Galerkin and continuous Galerkin pre-canned modules, and this would handle things like Fileio and a lot more of the higher level stuff that's really needed to have a clean application on the other side. So we've still got some work to do, but we made it quite far, and we were ready to start doing some benchmarks. Let's talk real quick about how we got HIPFort into the code. In case any of you out there are developing your own codes using HIP or HIPFort, this could be relevant for you, and certainly if you're doing any sort of Fortran C++ interoperability, this section is definitely relevant for you. So I'm going to kind of walk you through some of the basic ingredients that were necessary to have HIPFort usable in Self. So the bottom layer here, you have to write a kernel in C++. Or if you've written CUDA kernels before, you can actually leverage CUDA kernels just fine. The HIPCC compiler will interpret those. But at the bottom end of this is you have a kernel that's got this global. It's a global type kernel, meaning that it's a kernel that can be called from the CPU to run on the GPU. That specifies the instructions that need to be run on the GPU. In this example, I'm showing you just the vector DG divergence, as we'll be talking about this one in our benchmarks. If you've done GPU programming before, you're recognizing this already. For those of you who have not done this already, basically the thread IDX and block IDX intrinsics that come with CUDA or HIP allow you to reference the specific address of a single thread that's calling this particular routine. So when you launch with thousands of threads on the GPU, you can use those thread IDs to access specific slots in memory so you can get that parallelism exposed. So I'm not putting the rest of the instructions in here, but the bottom level ingredient so far is to write a HIP kernel. Next is we need a routine that's exposed as a C routine. That's really just a wrapper around that kernel. Here, all this does is it calls this HIP launch kernel GGL, which in the newer versions of ROCm, you can just use your usual CUDA syntax with the chevron syntax to launch your kernels. I had started this work before those features were out, but right now, so what this is showing really is we're launching that kernel that we wrote in that previous slide on the GPU in this wrapper routine. And the reason why we need to make this exposed as a C routine is so we can use Isoc binding in Fortran, so you can actually call the vector DG divergence GPU kernel on the from the Fortran side. So let's talk a little bit about the Isoc binding. The way this ends up working in Fortran is you have to define an interface that basically maps the inputs in Fortran and what the types of the variables are in the Fortran side to that layer there, so that on the Fortran side, the compiler knows how to actually reference that C routine underneath the hood. The big things here I just want to point you to is when you define this particular interface, you're going to use the bind directive here, and you'll bind that to the name of that C routine you have on the in that C++ code. Again, you're using that Isoc binding intrinsic, so inherently, if you want to run with self, you do need to use a Fortran compiler that's at least 2003 compliant. And we will be posting lists of compilers that we do test with if you're ever interested in that. And again, we're using those C pointers for all the variables that go across to the C side rather than Fortran allocatables. So once you have that interface defined, you now need to actually add a Fortran wrapper to call the C wrapper, which then calls the GPU kernel. And what that wrapper looks like, and this is where we really start to put in some logic to figure out whether or not we're going to run the CPU or the GPU. So you'll notice on this name, so I got the vector DG divergence again, 3D, and then I append the name of the routine with an underscore GPU. So there is a counterpart for this routine. It's the same, it does the same thing. It's got the underscore CPU on it, and it has the actual CPU instructions in it. And again, if you want to check out the code here, just look under the source directory and check out self Lagrange, and you'll kind of see how this lays out on the CPU side. But the idea here for the GPU wrapper is we're passing in the argument list, fdev, bfdev, dfdev, etc. All these are type C pointer. Okay, and then of course, if we're building for a GPU architecture, we call that GPU wrapper. In the code, what actually ends up happening is if you've not built for the GPU architecture and you try passing a C pointer in there, the code, the subroutine will just error out on you and tell you, hey man, you haven't built for a GPU, so don't use this interface. Now, to create the generic interface, right? So now you've got the Fortran wrappers. We've got the GPU version in Fortran, which really just calls that stack in C++ to get you running on the GPU. We have the CPU counterpart, right? And it's got the CPU layer, and instead the fdev, bfdev, etc. All those on the CPU counterpart are Fortran allocatables, and you can use this sort of pattern here in your type-bound procedures, where you declare a generic public for the name of the routine being vector divergence 3D, for example. And you can map that to both the CPU counterpart and the GPU counterpart. And then we, of course, make these private because what we really want users to use is this vector DG divergence 3D only. And in terms of the usage, this is how it looks when you call it in the code. It ends up being incredibly simple. And if the type of F and DF are both C pointers, this will run on the GPU. If they're both allocatables, it will run on the CPU. And if you mix them, when you try to do this at runtime, the compiler will probably catch that at build time. But the basic idea is we put in all this work to really make these interfaces so much easier, so you don't have to think about all the GPU programming underneath the hood. You can focus on, hey, I need to do a divergence, I need to do a gradient curl. And the stuff we're adding in these days is adding options for whether you're doing a weak formulation, whether it's discontinuous or continuous Galerkin, collocation, so you have those choices to make while you're programming with the self API. So that's how we got HIPFort in place. I want to talk a little bit about Fileio, and then we will get to benchmarks. So this has been an issue that's plagued me for quite a while, and especially in the Spectre element realm. There's not a lot of tools out there that inherently have higher order elements in there. There are some commercial software available that are really, really, really handy, but of course, if you have the funding to actually pay for that, I mean, you know where that gets you. But essentially we have, and I just put a short list here. You have things like Gmesh. If you're at Sandia, you're using things like Qubit probably, or the commercial counterpart for that is Trellis. Pointwise, again, another great commercial code that can do mesh generation and write out in a variety of formats. HOHQmesh, this is a code that it's just in the researcher network here. This is something from David Kopriva out in California, and from his times at Florida State. And then if you look into like codes like Nectar++, Nec 5000, if you look at Numa, every one of those codes sort of has their own sort of bespoke set of tools for creating meshes and making sure you preserve higher order information. The big issue with a lot of these tools out of the box is the highest order you can get is about third order. Okay, so if you have third order information for your boundaries, but you're using higher order solutions interior, you're already losing some accuracy or losing the benefit of going higher order simply because your boundary representations are not as high order. So there are some solutions to that, which is what we'll talk about when we talk about Hopper. But like I said, to top this off, all right, you got all these different tools. There's a ton of different mesh formats, and sharing data from one researcher to another is ideally, I think, where a lot of us want to be, where we could have teams of specialists running codes, creating output, handing that off to folks who are doing a lot of post-processing and a lot of the learning. Nowadays with machine learning, having data that's accessible across multiple platforms is more important than ever. But we have no shortage of standards and mesh formats that are out there. Of course, Gmesh has its own, and then there's CGNS, which comes out of NASA and some of the industrial groups in the auto industry. Now the cool thing about CGNS is they did just approve a new standard that's coming out in version 5 of CGNS to store higher order data. So it is good to start to see some of these more adopted systems take on a standard that's going to be more shareable across domains. But again, at the end of the day, when you're talking about researchers, you're trying to get everyone on board with using something at least similar enough to where the conversion is not an issue. Again, we got OBJ, VTK, we got something in NetCDF, and then down here is Hopper. Now Hopper is pretty cool. This was a project that came out of the numerics research group at the University of Stuttgart in Germany. And this tool primarily, it does have some mesh generation capabilities, but it also is capable of reading in a variety of common mesh formats and remapping those meshes to write them as higher order meshes. Pretty cool technology there, and of course they do have a file format standard for their code, because at the time that this came out, still everyone was kind of writing their own format for higher order data. Now the Hopper format turns out is pretty close to the CGNS CPEX 0045, the new standard that's coming out. So we're hoping that there's going to be some synergy here coming forward, where there's going to be some convergence in that specification. But at the moment, what we do right now is we leverage tools like Hopper itself for our mesh generation or mesh pre-processing to do some of the benchmarks I'm going to show you today. And then of course we pass those meshes into Self to do the actual calculations that we'll be benchmarking. So again, that general workflow for the CLI at this moment is the expectation is that you're generating a mesh from somewhere else, and at some point you're passing it through Hopper to get it into that Hopper format, because that's the only file I/O we currently support today. Then you can call the CLI and do some post-processing. Now, if you're developing with Self, you want to build your own application using the libraries, you would essentially follow the same workflow on the front end there, and then use we have an extension for the Hopper format so that you can include your vector scalars and tensors output in HDF5 files. But those APIs are in place. Essentially, right now you'd have to inherit this sort of workflow on the front end here with these two tools, or your mesh generator of choice, and in the Hopper preprocessor to build a PDE solver. All right, so let's take a look at some benchmarks. This for me is the most exciting thing, because basically for me this marked a day where I could tell you confidently we are getting the correct answers both in 32-bit and 64-bit precision. and we're getting the correct answer on x86 platforms, NVIDIA GPUs, and AMD GPUs. This was a big milestone for me. Wish I could have gone out and celebrated, but got to play it safe, so I had a little beer at home for this one. A couple weeks ago, we had a hackathon with OSHackathon, and I was able to get some time on a cluster called the OSHPC cluster. This is a cloud-native resource hosted on Google Cloud Platform by Fluid Numerics, our company here. And I got some time on the NVIDIA V100 GPUs here. And in terms of the software stack, if you're interested, we were working with ROCm 4.0.1 to give us HIPFort and HIP, CUDA 11 to offload to the NVIDIA GPUs underneath the hood, and we're running on CentOS 7. And for the AMD GPUs here, we're running on some systems that AMD generously donated some time on. The AMD Accelerator Cloud, we got some time on the MI50s and the MI100 GPUs. So let's talk real quick about the sort of the context of the algorithm that we're going to be benchmarking here. So when you're doing discontinuous Galerkin methods, for example, when you're doing a CFD solver, the dominant cost is primarily doing this divergence. You calculate the momentum, mass, energy fluxes, then you need to take a divergence of that, and then you usually have some other source terms. This takes up a lot of time. And in terms of doing that divergence, once you've calculated the interior fluxes, you need to do a boundary interpolation to prolong the solution onto element boundaries. You use the information on the element boundaries to do a Riemann solver, so you exchange fluxes between neighboring elements, or you exchange mass, momentum, and energy between neighboring elements by calculating fluxes. Then we do the projection onto the contravariant basis vectors, and then actually do the computational, the divergence in computational space. What we're looking at today in the benchmarks is just these last two steps. These, out of those four, are the two most expensive steps in that process. So here what I'm showing you is some of the run times, the average runtime per call to those two routines. So the way this works here is if you go from left to right, we're increasing the problem size. And in terms of the problem size, we're always using a polynomial degree of 7, which means each element has 8 by 8 by 8 control points in them. And we increase the problem size by increasing the number of elements. In other words, we're increasing the resolution. So going left to right, we're purposefully putting in more work and seeing how well this code scales on a single GPU. And then on the y-axis here, we're looking at the duration of each call to the two routines in milliseconds. So the combination of doing the contravariant projection and that computational divergence. Generally, where things have landed here with no special tuning, well, again, the big thing for me is I can run on multiple hardware and I can get the same answer, which is again very huge. So we have these three most expensive bars are the 64-bit. When we build the code with the 64-bit computations, this red bar here is the AMD MI50s, then we've got the MI100s, and then the V100s. And then down below here are the 32-bit calculations. And the nice thing here is on the 32-bit, if you can sacrifice some of the performance, you do get some significant performance gains. And also the V100 and the MI100 are actually fairly comparable at 32-bit calculations. We've got some work to do to figure out what the discrepancies are associated between the MI100 and the MI50s here. Certainly these are different architectures, so some more ideal tunings are necessary to get those, I guess, more optimized for each target architecture. And of course the difference between the AMD and NVIDIA hardware is another area we need to explore. Now if you look at this, if you basically take each of those runtimes and divide by the total number of degrees of freedom here, the total number of degrees of freedom here being basically those 8 by 8 by 8 multiplied by the number of elements. If you divide those runtimes by the number of degrees of freedom here, you get a cost, or in some sense a cost per node for these calculations. And the reason why we look at this is we want to see whether or not we're oversaturating the GPU. And what you would see if you're oversaturating or overworking a GPU is that the cost per node would generally climb. And here what we actually see is at least out to 13 million degrees of freedom, which is a fairly sizable problem. Things stay relatively flat across all the architectures we looked at here. And again, you really start to see that comparison between the NVIDIA V100 and the MI100 being fairly comparable when running at 32-bit floating point arithmetic. Now, the one thing I'm still trying to understand here is if you look at this yellow bar, which is the MI100 float 64 calculations, as I increase the problem size, the cost per node actually continues to drop. That GPU does still have a lot of memory left for us to actually expose, so we're planning on running these benchmarks out a bit further still on a single GPU to see how that behavior trends further out. So that's where we are today. Here's where we're going. Like I said at the beginning of all this, we've got some work we're doing on getting the MPI routines in there and the MPI plus routines in there so you can go on multi-node systems. You can run in parallel on x86 platforms. Of course, multi-GPU is definitely on our target here for the next quarter. We've got some of the Hopper Fileio I do need to wrap up here so we can expose. I think we're really just leaving out the vectors and tensors output on that, but most of that API is in place to read in Hopper meshes on the dev branch of self. And of course, we're keeping our eye on that CPEX 0045 merge into CGNS. So when that CGNS version 5 comes out, we'll be looking at getting that in place. As I said at the beginning, is where we left off in terms of the pattern-driven design, is where we have that self-map data. Now what I do want to do is extend that one more level and provide you a clean interface for doing continuous Galerkin, discontinuous Galerkin classes. And of course, we're going to add a collocation layer in there as well, if those methods are desirable. Basically what this layer is going to do for you is it's going to combine the map data, mesh, it's going to tie all that stuff together. It's going to give you a linked list setup so you can specify variable names and descriptions and all that metadata you want to store in those HDF5 files to make a nice clean interface to create a conservation loss solver or a PDE solver. So keep an eye out for that. We've got some discussion going on internally. I'm going to be posting those up on GitHub to try to get feedback from you on what you would like to do. And then where the other half of this is getting our continuous integration and continuous benchmarking a bit more robust. Right now, when we push to the GitHub repository, we check every single commit on x86 and NVIDIA platforms. We have plans to extend that to use AMD GPUs as well. And we're working on a neat system that will actually run through with profilers to get us complete benchmarks of all the routines and get those stored and publicly available for you to search through. So as you build your code, if you know you're going to make certain self API calls and you have an idea of your problem size, you'll be able to query that database to figure out roughly what your computational resource expenses might be. So keep an eye out for that. We'll be talking a lot more about that as the year rolls on. If you want to follow that stuff, certainly subscribe to us on YouTube, and I'll keep you posted on all that information. Again, check out that Discord server on the self repository, where you can chat with me afterwards and keep track of what we got going on. We are planning our official version release. We do have an alpha release out simply so we can mark the version where we did those benchmarks. But the official version 0.0.1 release will be coming out likely in Q3. And then I'll be building out rebuilding that self-fluids application using this entire API to also give you an example of how you could use the API for your problems. Again, if you want to learn more, check us out on GitHub, higher order methods /self. And then, of course, you can go to help.fluidmerics.com/self to see more of the technical documentation. We're actively working on putting new information up there so you have some theoretical background. If you haven't done Spectre elements before, we want to make sure you know what you're working with. And then, of course, if you're developing things with self, you can check out the higherordermethods.github.io/self that has all the API documentation you'll need to work with self. So that's it. If you do have questions, go ahead and post them in the chat. I'll be keeping an eye on that as best I can here. And again, if you have nothing for me today, definitely subscribe to us on YouTube to keep track of our updates, and check us out on the Discord server.